Hi, everybody. Welcome to GAAC.
Yeah.
Happy Valentine's Day. Tonight's speaker is Christina Andrade. She's at the Minnesota Institute for Astrophysics, where she's the head of operations at the Kilonova-Catcher core team, which is a citizen science project, which is part of the GRAMA program, which let's see, is a worldwide collaboration with the goal of studying gravitational wave sources and their electromagnetic counterparts. Please welcome Christina Andrade.
Hello, how is everybody doing today? I hope it's at least a little bit less snowy where everybody's at. Although Massachusetts, you never know. So I'll get started today talking about Kilonova-Catcher. It's a citizen science project, anyone can join, and it's dedicated to the discovery of the optical counterparts to gravitational waves and other fast transients. So what is Kilonova-Catcher a little more closely? It is a community of amateur astronomers, 189 current registered users in all continents. We have 159 individual telescopes and 14 remote telescopes that our astronomers have access to. We perform live follow-up observations of the optical counterparts to gravitational waves and fast transients, and I'll go more into what those are in a bit. So our members collaborate with professional scientists and contribute to the field of multi-messenger astronomy. That's what GRAMA is. GRAMA is a telescope network of professional astrophysicists and astronomers from across the world that then help and aid Kilonova-Catcher with follow-up observations. So we all work together to publish and contribute to multi-messenger astronomy. So what is multi-messenger astronomy? So multi-messenger astronomy is a field of study within astrophysics. And there are many ways that astrophysicists like myself, physicists, particle astrophysicists, and astronomers get their information about the activity within the universe. And so we have electromagnetic radiation or light. So, telescopes like Hubble use these. We have neutrino detectors like this one in Japan, which is a body of water with very sensitive filters that detect when a neutrino flies through. We have gravitational wave detectors called interferometers, which is what we listen to. And we have cosmic ray detectors. Now, I want to take a step back. And so that's how scientists detect things at a distance. How do humans detect things at a distance? So we use our eyes, which are designed to detect light. We use our ears, designed to detect a different type of wave, sound. And we use smell, which is designed to detect particles in the air. And you notice that these detectors look absolutely nothing like each other. Now we come back to this. Multi-messenger astronomy is the study of astrophysical phenomena through different types of cosmic messengers. We have our eyes to the universe, which uses light, electromagnetic radiation, like the Hubble telescope, the James WST. We have our ears to the universe, which are gravitational waves. We have our nose to the universe, which detects particles, like neutrino detection and cosmic rays. And so what does Kilonova-Catcher do? So we observe the optical follow-up kilonova to gravitational waves, our eyes and ears to the universe. What are gravitational waves? So what happens when two super dense objects merge? This collision releases such power that it perturbs the universe itself. Gravitational waves, according to Einstein, consist of an oscillatory space warp and oscillating stretch and squeeze of space. And so when there's a very big explosion, when two things hit together in space, gravitational waves occur. And they propagate throughout space-time. Kind of like how sound waves propagate throughout the air, they're compound waves. So a little closer look at gravitational waves. So gravitational waves are a disturbance of space-time itself. Mass affects gravity. And when that mass gets very hostile and collides into each other, all right, it disturbs or perturbs the entire universe. It makes it a little bit wider in some parts and a little bit longer in other parts. That's what a gravitational wave is. They travel at the speed of light, and they carry information about their source in their wave properties. So the angle with which two objects collide, the spin, the distance away that this event occurred, that information is carried on gravitational waves. And unlike light, gravitational waves are not as perturbed by other events in the universe. They propagate through it. And so they're extremely weak, requiring highly sensitive detectors called LIGO, Virgo, and Kagra, which I'll go into next. And the source of gravitational waves that we are aware of are binary black hole mergers, neutron star collisions, and supernova. So how do we detect gravitational waves? And so we do not use optical telescopes. We don't use the JWST. We don't use Hubble. We use a telescope. It's not a telescope. We use a machine called an interferometer. And so these observatories use mirrors spaced several kilometers apart to detect tiny vibrations from passing gravitational waves or oscillations in the diameter of our universe. Remember that squeeze and lengthen of the universe. They are capable of detecting a change of less than 1/10,000th the charge diameter of a proton. So we're talking a very, very, very small change in the universe is what these observatories, these interferometers are capable of detecting. So we have LIGO, Hanford LIGO, and then in Louisiana as well. So we have them in Seattle and Louisiana. Then we have Virgo in Western Europe. We have Kagra, and we also have Virgo India, which is being built.
To measure the stretching and squeezing, Ray turned to a device called an
Can everybody hear it?
Yes.
Yes.
Perfect.
interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected with the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
So when thinking about gravitational waves, a question you can ask yourself is, to what extent does one event interact with the rest of the universe? That is what gravitational waves are. Another way to think of a gravitational waves are like they're sound waves. Again, this is something I said previously. Sound waves don't carry matter, but are rather a response to it. They require a medium to travel. Sound waves can travel on the air. Gravitational waves travel on the universe itself. It is the interaction of one event with the rest of the universe. So what do we observe with gravitational waves? So why is astronomy a telescope network, both Kilonova-Catcher and Grandma, all right, looking at gravitational waves? Well, gravitational waves are like our flag, saying, hey, there's something going on all the way over there. You need to look for it. Look for what caused it. And that's and the thing that causes it are called kilonova. So Kilonova-Catcher is not an interferometer. We are a group of astronomers with telescopes. And so kilonova are not to be mistaken for supernova. Kilonova are powerful transient astronomical events. And transient means that they evolve. And kilonova in particular are fast transients, which means they evolve very quickly. And sometimes they can evolve within days, as in you have to observe within days or you don't catch it at whatsoever. Kilonova occur in compact binary systems. So that means that there are two stellar objects within one system or orbiting around each other via Berry point. So they occur in compact binary systems when two neutron stars binary BNS, as we refer to them, collide, when two black holes, BBH, as we refer to them, collide, or a combination of the two, neutron star black hole collide. They generate gravitational waves with unique waveform evolution and higher peak frequencies, binary neutron star mergers being the largest. So a supernova occurs when a star at least 5 times the mass of our sun explodes, releasing a lot of energy. A kilonova occurs when 2 neutron stars, 2 black holes, or a neutron star and a black hole collide. These are very dense objects. So why do we want to study kilonova? Why do we want to observe these things? Why is there this huge effort across multiple different forms of study, cosmic rays, neutrino science, optical observatory development, LIGO, Virgo, and Kagra? It helps us understand how matter behaves in super dense environments. Neutron stars are incredibly dense. Neutron stars occur when a large star collapses in on itself and all the protons and electrons all smash together to create neutrons. And it's a star made of complete neutrons. And so observing these phenomena, observing kilonova, especially binary neutron star mergers, right, help us understand how matter behaves in super dense environments. Kilonova produces the heavy elements we find in our world, such as gold and platinum, and they are faint and fast fading, rare cosmic events. So they're a great test to see how fast, how efficient our observatories are, both ground and in space. And so what do I mean when we do live follow-up? Well, we need to observe very quickly. These are fast transients. But why is it so important that we do live follow-up? You know, we're not just looking through archives for things, because we only have one complete detection, right? So the first neutron star detection, and the only one of its kind thus completed observation, all right, was in August 17th of 2017. And so 2 years before, we had our first black hole merger detection, which is great, but we can't see anything with black holes. They don't emit light. Neutron stars do. And so in August 17th, 2017, we detected our LIGO and Virgo's gravitational wave detectors, confirmed a gravitational wave by non-gravitational means for the first time, which means it was the first neutron star collision detected. The aftermath of this merger was seen by 70 observatories across all 7 continents and in space, across the electromagnetic spectrum, from UV, which is where kilonovas rise in, to the red and near infrared, which is what they fade in. This marked a significant breakthrough. For multi-messenger astronomy. A short gamma ray burst, designated GRB 170817A, was detected by Fermi in an integral spacecraft 1.7 seconds after the GW merger signal went out. And that's one of the things that made this so amazing, why it is so hard to reproduce, because not only were we looking in the sky at the right time to catch it as early as possible and get it in a full electromagnetic spectrum, in a full light spectrum, right? But we also detected the gamma ray burst and its afterglow. So what are gamma ray bursts? What are gamma ray burst afterglows, right? Gamma ray bursts are brief, intense flashes of gamma rays and X-rays that occur in distant galaxies. So after the initial burst, a longer lasting afterglow phase emits radiation across the electromagnetic spectrum. So we see it in X-ray, we see it in UV, right? We see it optically. And so GRBs are now associated with the same kilonova that generate gravitational waves. We only could confirm this with GW 170817. And so we are trying to recreate this. We are trying to simultaneously detect the GRB afterglow, the GRB, and the optical kilonova. So where does Kilonova-Catcher come into play? So a group of amateur astronomers armed with telescopes are working alongside professional astrophysicists to detect more complete detections. And just like we see all these things around a gravitational wave, the scientific program of Kilonova-Catcher also centers around these things. So our primary program, our core program, is the binary neutron star merger and the associated optical counterparts. So GRBs, GRB afterglows. And then we also do opportunistic programs, because binary neutron star mergers are rare events. And so we want our astronomers to not only contribute to science over time, but also to have things to do during the year. And analyzing gamma rays is really important. Gamma ray bursts and gamma ray burst afterglows is really important because sometimes the gravitational wave detectors do not catch the neutron star mergers. Multi-messenger astronomy, gravitational wave science is still very new. The interferometers are not perfected. We do a lot of machine learning with them, and we have to create events, manufacture our own events by varying parameters from the original detection in order to understand what is the limit of what we can detect, how far. Because GW170817 was relatively close at 40 megaparsecs, but the neutron star black hole merger that happened last week was 10 times that distance, which is phenomenally far. And so the job of Kilonova-Catcher, the job of GRAMA is to respond as quickly as possible to these gravitational wave alerts and to make sure that we are trailing behind on all the other possible flags of these events. And so what are the telescopes within Kilonova-Catcher? And so we have a median diameter of 0.32 meters, so about 12 inches. We use Johnson BVRI filters, unfiltered filters or no filters, and we use these Sloan Digital Sky Survey filters, 7 sets of them. And so how sensitive are these instruments? Well, remember that negative numbers are brighter events and larger numbers are dimmer events. And so we can reach 18 to 21.5 magnitudes with 30-minute exposures to 2-hour exposures in G, as well as in R, and then slightly brighter magnitudes at 16 to 17.8. And this is fine because GW170817 was able to be detected at 16.8 magnitudes, which is great. So perfect. Kilonova-Catcher can detect kilonovae. Wonderful. And so how do a group of amateur astronomers receive alerts? Well, the core team of Kilonova-Catcher, as well as the core team of GRAMA, are the same group of people. And so whenever, and we are spread across the world, so there's no concern about missing a detection because we're constantly on shift. And so the scientists of GRAMA will receive an alert directly from LIGO, Virgo, and Kagra. And now we've been able to synthesize this information so that the astronomers can receive the alerts immediately as well. So they don't have to wait for us to say, hey, why don't you go observe? And so we coordinate these observations with the amateur astronomers. We say, hey, we are looking at a 3-4 hour delay from the time that the gravitational wave alert went out. You need to start observing in your R filter, or we just got this alert. We need you to observe in your U and your bluer filters. Perfect. And we have people who then return these images, which is what we then synthesize. And so we'll send coordinates, we'll send redshifts, we'll send filter recommendations. All of this is done through Slack, so they get these alerts to let them know what's going on. And recently, we've been able to break down the information so that anybody who is maybe not be familiar with gravitational wave science can still understand what they need to do, where they need to look, and sometimes what places, multiple places they need to look. Because when we get these alerts, they have pretty wide field of view. Sometimes we have a 90% area to observe that's several megaparsecs wide. So hey, how do we focus on these? And so we help the astronomers by tiling or doing galaxy targeting, saying, hey, we suspect that it's in this galaxy over here. We send them coordinates, especially if we have, depending on where the location of the telescope and the amateur astronomers are. And so Kilonova-Catcher, the website, also has a trigger alert system, so you'll get emails through there. We will send, if it's not being ingested through Sky Portal or through the Kilonova-Catcher website, we don't have to worry about that because sometimes we just send it directly to you guys. And that could mean that, hey, this information was given outside of the alert system directly to a scientist like myself or the PIs, and we trigger them independently. So sometimes these amateur astronomers are receiving information that not even the public has received in order to observe early and quickly. And so this is our astronomer guide, and don't worry, I have a link for you guys to be able to get a lot of these, the astronomer guide and how-tos at the end if you're interested in joining, which I implore you, please join. We are looking for new members. We are looking for more coverage within the United States, and we are looking for people who are really, really interested in being part of frontier science. And so this is part of our astronomer's guide, which teaches you how to use the Kilonova-Catcher website to upload images and to get information. And if you don't want to do that, you're like, hey, it just goes directly to my email, so I'm just going to send it to you. Perfect. Makes it a little bit easier for me because I can just synthesize the images straight from my email. Perfect. And so I've kind of thrown you guys a lot of information, and this is kind of the summary of what we do within Kilonova-Catcher. And so we receive GRB alerts from the NASA's General Coordinates Network, which is called the GCN. We also have alerts that are ingested directly into Slack from Sky Portal, which is think of it as like the Facebook for transient events. So it's where the scientists, on the scientist side, will put all the information that comes from the professional and amateur telescopes. And so we then use the information that we have been triggered with to alert KNC. We coordinate the telescopes based on who's experiencing day, like these dark areas here, or who's experiencing night by these dark areas here, or day by these yellow areas here. And so then you can upload images. And so you see that these are all from Mark Sereau, and he was viewing a lot with this, which is great. And then we can upload photometry. And so that means we extract magnitudes and distance and a magnitude error, which is how bright is this object that what we're looking at? What is the light coming from it? What color is the light coming from it? And we can upload it to Sky Portal. Remember that Facebook type thing where we can see each individual event, and it produces a light curve. And this light curve is the end goal. It is the end all be all of what we're going for. There are professional telescopes on there. There is, professional general coordinates, like from the General Coordinates Network, the professional GCNs that are on there. So Swift, Fermi, ZTF satellites, right? All of their information is on there, plus the amateur astronomer telescopes, plus the professional telescopes within Grandma's network. And so they all contribute to this light curve. And so we want this for every single binary neutron star, every single neutron star black hole merger. We want these for every single gamma ray burst we observe. And this is what we're going for, to get a complete light curve. So we know what is occurring in this event because, again, there are connections between the waveform evolution of the gravitational wave and the light curve at the end of this, because we can tell the spin, if there was gas around this environment. Let's say there was a black hole. Was there an accretion disk around the black hole when it collided with the neutron star? How big was the neutron star? So what does happen during the year? What do we do with your data? What do we do with your images when you participate? We publish you guys. So first of all, you guys contribute to the entire community of scientists that observe these fast transients or any transient. And so for IceCube, when there was a neutrino detection, remember those particles, all right, another messenger that we received, we had Kilonova-Catcher observe its progenitor or its source, what caused those neutrinos to be released. All right, we had an X-ray transient. Something was evolving in the X-ray that we detected. Kilonova-Catcher and Grandma were able to participate together. All right, when there was a gravitational wave event, we didn't find any significant candidates, but we were able to follow up with professional scientists alongside them. All right, and then look at all these GRBs that came afterwards, where we got detections, where we got an afterglow, which is so important to studying kilonova and gravitational waves and understanding our universe in a complete sense. And each year we look to publish 2 to 3 papers with, of course, with the Kilonova-Catcher contributors on it. And so the paper that I led was on a type 1A supernova, and it was a thermonuclear runaway with a lot of carbon and oxygen. This occurs when a carbon-oxygen white dwarf, so a white dwarf star that is made of carbon and oxygen primarily, it exceeded the Chandra-Shakar mass, which means that as it was doing nucleosynthesis, it could no longer outwardly produce enough energy to compensate for the size that it was already at. So that's the Chandra-Shakar mass limit. And so it accreted mass, it got too big, it exploded, type 1A supernova. And we were able to get a light curve and the secondary peak from it, which was amazing. And this was an event that we had not seen before because there was a lot of unburned carbon. Why would there be unburned carbon in a thermonuclear runaway event? That's amazing. How dense was this object? How big was this white dwarf? Did it exceed the limits that we thought white dwarfs could exist at. And so that's why these events are so important, because they help us understand what's going on in the universe with clarity. And so I kind of want to go back to this really quick. Notice how many data points KNC contributed, 337. All right, that is a third of the data point that they were able to collect. KNC sometimes can observe when larger telescopes cannot. And so together we have done some amazing science, amazing frontier science. And we were able to publish 2 papers, one alongside the Jinglong Observatory in China, which was a wonderful collaboration. I headed the paper for that. And then we had a Astronomical Society note, which just focused on the contributions of grandma. And so if you guys want to scan the QR codes here to read these papers or to get a little bit more of an understanding of what this event was, you're more than welcome to scan the QR code. I'll give you guys a minute for that. And I'll also send this, Say that again?
We'll be able to scan those from the video if we want to.
Cool beans. All right. So that's the information I have for everybody. Here is another QR code to a Google link, which will provide you with all the information you want if you want to register for KNC on the website. If you want to join our Slack and contact me directly, we have a very active, very open community. We all talk to each other. There's no titles or anything like that, astronomer to astrophysicist. I even have 2 amateur astronomers helping me write the guidebook for new members. Like, how do they pre-process? What do they use for the people in Europe? What do they use? For the people in America, what do they use? How do they differ? How do we help everybody participate? So very active community, please join. If you want to read the Astronomer's Guide more closely, that's also on this QR code. And we also have our frequently asked questions, which will provide more in-depth analysis of what multi-messenger astronomy is and what kilonova are and what GRBs are. Thank you so much. So I'll take any questions if you guys have it. I see a few people applauding. I appreciate it.
Thank you very much.
Yeah, could we get could you stop sharing and we can have some questions from the online people and so on. Here we go. Hang on a minute. Why is that doing that? I don't have any idea.
Christina,
Yes. Who's speaking?
do gravity waves always precede other events from that area? Is that a way you get a direction of where you're looking?
So gravitational waves can come from any point in the sky. But they always come from they propagate from the area where the kilonova occurred. They propagate from one direction, but through the universe.
Well, when 2 black holes collide, you get a gravitational wave. Can you tell it happened over in a certain direction from the detection?
Yes.
How accurately?
It depends on the event. It depends on the factors around the event. So like for black holes, for example, if there's accretion disks, if there's, depending on the size of the black hole. So black holes, when we observe gravitational wave events with black holes, which we can, because sometimes there's accretion disks,
Questions?
I have the technical expertise, I have the numbers, but I'm trying to process this in a way that people who may not understand, these numbers could have an instinctual kind of understanding of this. Restate your question.
Well, can you tell what direction it came from?
Yes. So the larger the black hole, the louder it is, the higher the amplitude. So binary neutron star events are really dense. There's a lot of matter. There's a lot of matter involved. So those are going to have the largest frequency gravitational waves. And so it's kind of like a blip, like when you look for like sonar. All right, we're able to tell directionally. Binary black holes that don't have an accretion disk, when there's very little matter interacting, will not be as strong.
Okay, great. That's strong. Sure. Thank you.
All right, Mario has his hand up. Mario?
Yeah, thank you. Nice talk. Can you hear me?
Yes.
Yeah, okay, great. So the question I have is, does gravitational waves follow the inverse square root, the square root, yeah, well, not square root, the inverse square law as they propagate?
No.
In other words, they don't. So you can't go by the strength of the signal then to estimate its distance, is that correct?
Yes.
Interesting.
Well, it can, but it is not dependable. Because if there is something large in the way, think of it as like the expansion of the universe. The objects on the universe, on the space-time, fabric of space-time, do not get larger. All right, so the entire universe is moving to compensate the for the energy that was released. So it does not follow an inverse square law. Not
Interesting. In the 90s, I was part of an AAVSO program to do optical follow-ups of gamma ray bursts. I didn't know if that was still being followed now.
Say that again. You broke up there.
In the 90s, 1990s, I was part of a group with the AAVSO that was chasing gamma ray bursts. And I imaged about 9 of them myself. But yeah, afterglows. I didn't know any group was still following gamma ray bursts.
That's cool. Yeah. So we still collaborate with the AAVSO with the French version of that called Colibri. Still work with them, and we still work with their members too.
You might pose that you need some observers through the AAVSO since it's a worldwide network if you're looking for observers.
Yes, I've been in contact with them. It was an
Good.
interesting interaction, and I'm going to follow up for a presentation with them. And also coming back to your inverse square law question, I think I answered incorrectly because when it does diminish, it does slow down as a factor of its distance away from the object.
Okay. Thank you.
But it does not, you cannot see it. You just see that the wave starts to very slowly dim. So the intensity of a gravitational wave decreases with the square of the distance from its source. However, there's one aspect of the wave that does not. And I always forget what it is. I do long duration gravitational wave detections, and we have no idea what those progenitors are. This is an ongoing study.
Thank you.
Thank you, Mario.
All right, Christina, you mentioned a list of telescopes that are responding to these gravitational wave observations, and you mentioned the Swift. And I was wondering if there are others up there with that same kind of response time, or if that's unique. That are built specifically to respond quickly to an.
So that is a loaded question.
You're welcome.
Because this is what we call time domain astronomy or target of opportunity astronomy. So the reason why I listed those telescopes is because those are the ones that will do target of opportunity, which means, hey, there's an alert, we want you to observe, which means that whatever survey they're doing, whatever they're observing, they stop and move. Getting JWST, Hubble, and then eventually Roman to do that, we've been trying. It doesn't work. For the Vera Rubin Observatory, which I am developing, its Kilonova detection algorithm as part of my research. Yeah, there is no target of opportunity system or plan right now to respond to it. So if you happen to be looking in that direction as a Kilonova, great. But this is where Roman comes in, when Roman launches into 2027, because Vera Rubin is doing a survey, which means that it's going to be viewing the optical sky completely every 3 days for 10 years. All right, so if we happen to get a gravitational wave alert in that area, great. We can observe it. But if it's not looking in that area, Vera Rubin is not going to observe that. Roman, when it releases though, is going to have such a wide field of view that the images that are being taken in that moment, we can then use over that time. So it'll start to create an archive, which has not been done before in space with such detail, because the Hubble cannot necessarily do it at this depth. JWST can, but not in infrared, and that's how these evolve very quickly. Roman cams. We're very excited for Roman. We're very excited for Vera Rubin when it comes on in May. For at least to kind of be able to serendipitously observe. It's very, very pessimistic. So there's not a lot of telescopes that can observe on trigger.
Okay, I thought not. I wanted to ask though. Eleanor, you have your hand up.
I do. Hi, Christina, and thanks for speaking to us. We look forward to having you at our club in Florida in a couple of months. The GRAMA website lists the partners and the team. The team, there are many, there are dozens of team members from all over, Azerbaijan, Georgia, the UAE, Iceland, China, Ukraine, a number from Ukraine. How does the team dovetail or work with the partners? You've got partners,
that's
but
grandma. So
that's
grandma.
Aren't affiliated with the partners.
That's a more of a like academic question, like faculty question. So if we have so we have the telescope teams. The ones you listed were the telescope teams, and they have observers with them and astronomers. And they will do shift work on shift in a designated time slot. But then there are these scientists involved, and the scientists involved are trading their expertise, the expertise of the individual or their students, for access to the information, access to publication, and for to help grandma maintain shift at all times.
Okay.
So you have the telescope teams, and then you have the contributing scientists.
Okay.
So they go through an institution, and usually it's through funding. So, hey, I'm being funded to look up gamma ray bursts. I'm gonna go work with grandma.
Thanks.
Christina, who came up with grandma, and could you tell us very slowly what it means?
Yes, absolutely. I love this question because it's funny. So grand, rapid, advanced network dedicated to gravitational wave, and gravitational wave is one word technically, astronomy. At the beginning, it was the Grand Rapid Advanced Network dedicated to multi-messenger ADICs, but we felt that was not very nice when we went big picture. So we kind of adjusted that to astronomy.
That's the grown-up one. Okay.
Yeah.
Yes, I have a question.
Yeah, we have a question in the room.
Yeah, hi. I just wanted to be sure that these gravitational waves, are they bidirectional or are they directional? And that's a question linked to the attenuation with distance too. If it's omnidirectional, I suppose that you have an attenuation with the square root of a distance due to the spreading. If it's directional, it's another story, and I don't know anything about gravitational waves, and that's why I'm asking.
So could you, I'm having trouble understanding you because of the static.
Oh, okay. Are the gravitational waves omnidirectional or directional?
Omnidirectional or directional?
Directional. They come from a source, a point.
Yes,
come
but
from a
do
point
they
source.
spread 360 degrees around, or are they going in a direction?
Do they radiate in 360 degrees or in one direction?
They radiate in two directions. So as the gravitational wave occurs, there's like a jet. So think of the jet as like gravitational wave. It does kind of create like a belly motion, but because the universe is like overall flat, it'll have strength in two directions. That's why if it's really important that the kilonova occurs within our field of view, wherever we are on the planet. That's why we have widespread interferometers.
Okay, thank you.
All right, thank you. Quite more questions in the room?
Yeah, I've got one.
Okay.
Hello, Christina.
Well,
Beginning of your program, you mentioned how the laser beam is split and sent off in two different directions, then it returns. How long of physical distance are these tubes, you call them initially? The arms.
Several kilometers.
I'm sorry, say again?
The arms of the interferometer are several kilometers long.
Okay. Thank you.
Oh, you're welcome. I like these questions. These are very good questions.
And they have to be straight and flat, yes.
Well, the universe is assumed to be flat just because of how it's expanding. So technically, yes.
Any other questions online? Alan, nothing from you?
Nope, I'm just here enjoying this great program. Thanks.
I got one. Does gravity interact with dark matter?
Yes.
How do you see
Dark
that?
matter affects gravity, but that's a cosmology question. Dark matter, gravitational lensing. So there's such a thing called the bullet cluster, which if you give me a moment, I can actually probably find a presentation where I describe this. But dark matter is ever present, and there are actually wells within the universe of dark matter, and it tends to coagulate around large groups of galaxies. So large neural networks of groups of galaxies orbiting each other. And so we were first able to understand, like with a direct observation, how dark matter interacts because of the bullet cluster. And so what happened was, let me see. Okay, I just found it. Give me one moment. If I didn't like the excitement of gravitational wave and kilonova detection, I would be a cosmologist, because the study of the large structures of the universe is really cool.
It sure is.
And so gravitational lensing occurs when there is dark matter and then a large object all in line with one another. And so what happens is that there's this curve of light when you're looking in this direction, and then you observe what the light source is, and it makes no sense. Why is it warped to that degree? There isn't enough matter there to do that. So the difference between the two is the evidence for dark matter. So I mean, Alan, you had a question.
Yes, I do have a question after all. It's because I think I missed a tiny minute of your presentation at the beginning. How common, how often are these kilonova events actually happening? I know we have to be looking at them or we miss them, but how often do they go on?
That's an offensive question to somebody like me, because I don't like the answer. But in all seriousness, there have been 5 kilonova with a neutron star in it, so binary neutron star or neutron star black hole collision, since the beginning of the first operating run of LIGO, Virgo, and Kagra, the gravitational wave detectors, through its 3rd operating run, and we're in the 2nd year of the 4th. So there have been 5 gravitational wave detections with a neutron star in it for the last 7 years.
And is that all of them, or that's all that we have detected?
Those are all of the ones that we were sure had a neutron star in it, because there have been others, but we could not observe.
And how many of those would you estimate? Can we estimate? Do we have any idea? These might be dumb questions. This is total layperson question, but.
So we get about, so 16 out of 130 detections have been false. So there is a ratio of, like, okay, the gravitational wave interferometer got it completely wrong. But the other issue is that sometimes the detector isn't sensitive enough for the event, the neutron star event that occurred. So we cannot get a good localization, like where is it on this map? We can't observe. So it's like roadblock, you get kicked off the road, roadblock, you get kicked off the road. I've done estimates with other observatories, such as the Vera Rubin, which is the largest ground telescope. And my optimistic for the most stringent criteria, which is 1 magnitude rise per day, 0.3 fade rate, magnitude per day, was 14, optimistically over 10 years, which is roughly 1 or 2 a year. The pessimistic wasn't even 1. And that's based on the binary neutron star detection rate from the last observing run. And then the median was 6, but that kind of makes sense given the last, 3 observing runs that we've had for LIGO, Virgo, and Kagra, the interferometers. Since you have an astrophysicist with you and I get to talk about cosmology, I'm going to answer this question. So the bullet cluster was kind of our first evidence that dark matter does interact, does have some presence with space-time, with mass and gravity. And we think it's because dark matter is made out of super large particles. And so this kind of explains that. And so the bullet cluster is a system of 2 colliding clusters of galaxies. The name bullet cluster refers to the smaller subcluster moving away from the larger one. The bullet and its gravitational lens are the 2 greatest pieces of evidence for dark matter in natural history. And so what is this really telling us? And so the blue area represents where most of the mass of the cluster is. And the bullet cluster is where the hot gas, where the baryonic matter is, where the actual matter that interacts, the atomic matter is. All right, baryonic matter, all right, not dark matter, you, myself, the table of elements, the periodic table of elements, that is what the pink stuff is. All right, the blue area here, let me can't see my finger, here and here is where most of the mass is. And that's because the gravitational lens that warps all that light is pulling the light this way. We're seeing more light over here instead of where the actual mass is. And we're like, what the heck is going to be doing that? And so that's where we were able to prove dark matter exists, because there was this displacement where the actual matter we could see was and where it was being warped. So this is a video that shows how, so when these 2 clusters of galaxies interact and all the gas is in one spot, you can see how the gas interacts and creates this bullet, but the dark matter barely shifts. However, it does it enough that at great distances, we can see the light being warped around it.
Wow, thanks.
Yeah. So this is how this is a 3D kind of look at it. And so notice how deformed the hot gas is compared to the dark matter. Remember, this occurs very slowly over time. Yes, Alan.
This is also fascinating. I had one other question. I don't want to pull you off of this yet, but I've just seen in my headlines as I've been getting online lately, for the first time, we actually see space move. And you made a reference in your presentation to last week's neutrino star and black hole merger. Is that what everybody's talking about? I haven't gotten to read any of those articles yet. I just keep seeing JWT see space move for the first time.
Yeah, so this neutron star black hole detection has something to do with that. It created a whole bunch of fuss, like releasing mice into close quarters reaction. And so seeing space move is a gravitational wave. And so the significance of the neutron star black hole detection that we had was that it was, first of all, it wasn't very close. It was poorly localized. We couldn't really get a handle of where it was, but it was bright, right? Because we were seeing 19 when we usually get like 18 to 21. We were seeing 19 magnitudes, which is pretty significant for a neutron star black hole, which means the black hole had to have an accretion disk for that matter to interact with it. However, there was no candidate, so like where we could actually see it detected. So we don't know if it was a blip on the screen. Asteroid happened to cross paths with people observing while the gravitational wave passed through, so it kind of created this shiny spot. We don't know. An asteroid passing a little too close could have also caused like a disturbance with LVK. And I'm not sure, I don't know too much about that, but I remember one of the gravitational wave interferometer engineers who works on it, she was telling me about this. So they're still trying to study the wave evolution without any optical counterparts to see why it triggered as a neutron star black hole, why it stayed there, and then why nobody could find anything. The issue was that it was 10 times farther. It was 40 megaparsecs for the one that we observed, GW 170817, and then GW 250206 DM, which is the one that occurred last week, was 10 times as far. It was like 400 megaparsecs. So we were observing like 20 different galaxies. There was a lot going on, a lot of data being exchanged. Kilonova-Catcher was on for like a week straight. Nobody detected anything. Nothing of significance anyways, nothing that had enough of an evolution. Because in order to say, hey, you detected a kilonova, you need to have at least 2 to 3 detections in 2 different filters. And we didn't get that.
Thank you. Fascinating presentation.
Thank you.
All right. Thank you. Any more questions online? All right.
I had a question.
All right, Elaine.
For all your formation of gravitational waves, you've had 2 things colliding. Is there ever 3 or more things colliding?
We have not yet detected that, because to have enough matter, enough of the right circumstances where you have 3 neutron stars, or even 2 neutron stars and a black hole, or 2 black holes and a neutron star, would have to be a massive stellar nebula. And the stellar nebula is basically what creates stars. So there was only enough hydrogen in our stellar nebula to create the sun and then our gas giant. There wasn't enough matter within the nebula, enough hydrogen to cause nuclear fusion within Jupiter to create a star. So if there had been a little bit more hydrogen within our stellar nebula, we would have had been a binary star system. However, neutron stars are the evolution of large stars. And so to have enough matter for large stars to form, and then 3 of them, without anything happening to create that environment, is exceptionally rare. We have not detected any, not that I know of.
Thank you.
All right, any more questions anywhere?
Eleanor, do you have a question? I thought I had seen somebody's hand up a few minutes ago. Okay, perfect.
We'll let you get some rest.
Thank you.
Thank you, Christina.
Thank you. Thank you, Christina.
And thank you for the sweater. I'm so sorry I was not wearing it. I had rushed in and thought getting here was more important, but I have worn it to school to work, and I've gotten a lot of comments on it. They think that you guys have a great logo with the planet, and then the sail ship, the sailed ship in front is amazing. So I really enjoyed that, and you guys should be getting some stickers and a card from me in the next few days.
Hey.
Thank you so much.
Thank you.
you very much for this. It was
Bye.
brilliant.
Yeah, if you ever want me to invite me back, I'd be happy to.
Have a great weekend.
Thank you.
And
You too. Happy
please
Valentine's
stay
Day.
safe,
You as
Christine.
well. Stay warm. Thank you so much.
That's all right.